each successive wave will tell the gas that initially is not moving at all. Now you need to expand. The next wave comes, you expand more. The next wave comes, you expand even more, right? So your dP becomes negative, while the gas is being moving along with the piston to the left, also negative. So what happened here is, intuitively, you should be able to figure this out. If you have a compression wave, it's moving, it really, the wave, okay, if this is the piston and this is the wave, the wave is the compression wave. It actually, compression wave carries the gas behind it along with it. Initially, it's not moving now, I pass it, once I pass the gas is following. Make sense? So conceptually, using this one-dimensional tube, you know that very, very well. But now, if I expand, if I pull it to the left, like for the expansion, the wave is propagating in that direction, but the gas is moving in that direction. So that means what? If I'm an expansion wave, I move in that direction, and the gas passing behind me will leave me. Make sense? Now, here you just talk about traffic, you will see that. If you have, let's say you are driving along outside of university, and the signal turns to red, so all the cars will stop, right? Makes sense? So how do you know you need to stop? If you don't stop, you're running through the car. So you know the signal is there, like, oh, okay, stop. Next car stop, right? So what happens is that your wave propagates in that direction. You see the red line. Your wave propagates in that direction, right? And the wave propagates in that direction. The car initially has a speed. Once the wave passes the car or the driver, he follows the rule, he stops. So the velocity decreases, right? Makes sense? So, relatively, if let's say you have a wave relative to the wave, the car speed actually decreases. Right? Makes sense? So, there is a velocity acting in that direction because the car is coming in that direction, and now there is a velocity acting in that direction. Right? So that means that active velocity really is caused by the wave. So if the gas is not moving initially, when the wave passes, it adds a velocity in that direction, so it's following the wave. Make sense? And now, once the light turns green, you go, right? And the wave passes in that direction also, because you are waiting here, you know, the car in front of it is moving, then you continue to move, and the next one will move after you move. So your expansion wave propagates in that direction, but the car goes in that direction. Right? So in this case, expansion is a better example because the wave propagates in that direction and the flow goes in that direction. Make sense? And you flip it, that will be the compression wave. So, how nice, right? So every day you are seeing compression wave and expansion wave in the traffic. So think about it today when you drive. Unless you are so lucky, it's all green light all the way to your home. Otherwise, you're not going to experience it. And just try to translate it, see if you can explain this. You know? Every day, anywhere on campus, you learn about your engineering. You see the sprinkler, you see the water going, streamline, straight line, path line, streamline. You know, you think about it. Everything is in here. It's really nice to be a mechanical aerospace engineer. Make sense? Okay, now, then we are down to analyzing it mathematically. So these are the conceptual things, right? This is what happened. Now, how to do the analysis? This is your shock wave. And you have a flow coming in. L1, T1, V1, M1, of course, has to be greater than 1. So I draw a control volume. Of course, this is an interesting control volume because suppose if we are looking at one-dimensional shock wave control volume, very thin, right? But that's okay. As we go out, we have P2, rho 2, T2, P2, M2. Again, as I said, what should we do? If I want to relate the velocity or all these properties to the upstream condition, right? For example, so far we have only been talking about what if shock wave move around, you know, move in this direction, the expansion wave then will move in the other direction. That's all qualitative, right? But we want to get quantitative. And what should you do? Continuity, right? Momentum. Energy. The reason that TT1 is equal to TT2 across shock wave, unless there is a heat loss, otherwise the total temperature will be the same. Okay, so we are going to manipulate this somewhat. So let's say you put in P equal to rho RT. Assume it's ideal gas. DH is equal to Cp constant Cp. And A squared is equal to gamma RT. What you can do here is your P1 plus, because your rho is equal to P1 over RT1 times V1 squared is equal to P2 plus P2 over RT2 times V2 squared. You multiply the gamma here, and divided by gamma, multiply the gamma and divided by gamma. This becomes N1 squared. This becomes L2 squared. So this will become P1 plus gamma P1 M1 squared is equal to P2 plus P gamma P2 M2 squared. So P1 times 1 plus gamma M1 squared is equal to P2 1 plus gamma M2 squared. This keep in mind. And rho 1 V1 equal to rho 2 V2 becomes P1 RT1 V1 squared equal to P2 RT2 V2 squared, V2. Now, this will become, that's only different, so, right? So this will become what? This will become P1 gamma RT1 V1 gamma RT1 equals P2 square root RT2 V2 RT2. Yeah. But V1 is equal to M1 square root of gamma RT1. B2 is equal to M2 square root of gamma RT2. So after some manipulation, it's actually only one step away. So you have P1 M1 over square root of T1 equal to P2 M2 over square root of T2. This is your continuity equation. So we are manipulating, right? Now, you ask me how do you know you need to go down that route?
Oh.
Well, of course I do. I know I only learned it, right? The key thing is that since we are talking about supersonic flow, we want a Mach number. So we want to massage everything so that it somehow contains a Mach number, right? So that's your continuity equation. And then, because your TT1 is equal to TT2, T1, 1 plus gamma minus 1 over 2, and 1 squared is equal to T2, 1 plus gamma minus 1 over 2, and 2 squared. So, then continuity becomes, you can easily show, because your continuity now has the square root of T1. So you have square root of T1 and square root of T2, and you square everything and make them be the ratio. So your continuity becomes M1, 1 plus gamma M1 squared, square root of 1 plus gamma minus 1 over 2, M1 squared is equal to M2, 1 plus gamma M2 squared, square root of 1 plus gamma minus 1 over 2, M2 squared. So eventually, you find out M2 is equal to M1 squared plus 2 over gamma minus 1 over 2 gamma minus 1, M1 squared minus 1, M2 squared. So this is your M2. And M2 less than 1 or M1 greater than 1. No solution if M1 is less than 1, mathematically. Wow, this is really nice, right? Somehow you find M2 based on M1. And gamma is the property of the gas anyway, right? So for a gas, for a given gas, if I know M1, I know M2. I said, well, there is no sharp rate in there. How do you know there is sharp rate? And there it is, right? Because we are using conservation of momentum, conservation of energy, and conservation of mass. If these are all satisfied and you come down with this, you almost have to believe it. Right? Well, assuming that your mathematical operations are correct, your algebra, everything is all correct, right? Because it's going to state that we may have something that's not possible. But let's say you use the 3 conservation laws and use the correct math. This is what you have. And you can go and plot it out. I mean, even gradient calculator can do it, right? You have this equation and plug in N1 all the way from 0 to... See, N1 just simply cannot be 0, you think about it. Because it's equal to 0, your numerator will be positive and denominator is negative 1. Obviously, there's no solution, right? If you just use the extreme condition. If you plug in, let's say, 0.8 for N1, that means your M2 will be an imaginary number, right? That you cannot use. So the only way for you to have solution, the real number solution, is that M1 has to be greater than 1, and M2 has to be less than 1, which is, go simply plot this thing out. Why don't you do that just to convince yourself? You don't want to believe me, right? Or you very much like to believe me, that's fine, but different from you convincing yourself. right? So any spreadsheet software can do it, right? So you plug it in and say, hey, the only solution will be when m1 is greater than 1. And even that's the case, your m2 has to be less than 1. So supersonic flow will become subsonic after shock wave. That's the and later on we will try to do that E over E1.
Say hi. Hi. Say hi to YouTube.
Yo, what's up YouTube?
What's up, YouTube? Alright.
You been in a room?
Yeah, alright.